So F wall x for one particle was mp times Vx squared divided by d, but now I want to look at it for all particles that have some component in the x direction. So that's going to be equal to mp times Vx1 squared over d plus mp times Vx2 squared over d plus all the way up to our last particle, which we'll say is the capital Nth particle, Vx capital N, well, plus mp Vx capital N squared over d. Okay, so we're going to factor out the mp over d, because each one of these has a contribution to hitting the wall. Each one will give a certain force to it based on its speed, as we realize here, but their speed isn't going to be the same value. So we have mp over d times Vx1 squared plus Vx2 squared plus Vxn squared. So how can we possibly deal with all these v's? Well, we know they're going to be in some distribution of v's, and so we can write this, instead of looking at each individual v squared, as the average v squared that one of the particles could have in the x direction. And how do we write the average for the v squared? V squared x, so the average of the squared velocity in the x direction, so it's not v average squared, okay, it is actually v squared averaged. That is equal to 1 over the total number of particles times Vx1 squared plus Vx2 squared plus Vxn squared, which is exactly what we have here, except for this factor of n. Okay, so we can rewrite this to take into account n number of particles, all our particles, by subbing that in here. So this means we can write this as mp over d times n Vx squared average. Okay. So this is what happens for all particles acting in the x direction. But now we also don't want to worry about just the x direction. As I said, the particles could be moving randomly in the y direction and the z direction as well. And so we don't want just x here. We want an overall v. We want the resultant vector here. So we have to remember that an overall v squared is equal to vx squared plus vy squared plus vz squared. If we're dealing with 2 dimensions, remember that the Pythagorean theorem says that the component in the x squared plus the component in the y squared gives you the hypotenuse squared, which is the resultant vector. For 3 dimensions, all you have to do is just add on the other part and square that as well. So the resulting vector here would be vx squared plus vy squared plus vz squared. And this is true for this statement, and also if they're averages. That works out as well. Now, the x direction is not going to be special compared to the y direction or the z direction. We just picked that one to work with. We could have been doing the whole thing in y. We could have been doing the whole thing in z. And so what that means is that vx squared average, because it's not special, will have to be the same average as vy squared, which will be the same average as vz squared. So that means that this equals vx squared, and this equals vx squared, and so the average of v squared is 3 times vx squared. Why did I want to do that? I wanted to do that because I want everything to turn to vx, so I can get rid of this vx. So now that I have this, and I know that the f of my wall here is equal to this in the x direction, I can now look at everything that's not in the x direction and the x direction as well by plugging in this over 3 for the vx squared. So now I have F, the force acting on the wall, okay, due to all particles, because we're dealing with capital N here, is equal to mp over d times n times 1/3 of v average squared. Okay, just plugging in that for there. Okay, so it's the force acting on that wall. So, I'm going to rewrite this a little bit, so I can put the m and the v next to each other again. So we have n over 3d times mp v bar squared. And I said I wanted to write this in terms of kinetic energy, which is 1/2 mv squared, and so I want to rewrite this as 1/2 mv squared. If I multiply by 2 over 2, I can do that. So then I get 2n over 3d times 1/2 mp v bar squared, or v squared bar. Okay? And this equals the force. But what is the pressure? The pressure is equal to the force divided by area. And what's the area of our wall here? The area of our wall is d squared. So that means that we have F wall divided by d squared. So that's 2n over 3. This whole thing divided by d squared means this d becomes cubed. This is d cubed times 1/2 mp v squared. So the pressure here, P, is now equal to this. And what is d cubed? D cubed is the volume of our cube. So P is equal to 2/3 n over v, put a little serif on it to distinguish it from the v there, from the velocity. It says that the pressure is equal to 2/3 n over v, the volume, times the average kinetic energy of your particle, of whatever particle is in your box. So now we see that since P is equal to 2/3 n over v times the kinetic energy, that the kinetic energy, if that goes up, the pressure goes up if the volume stays constant and the number of particles stays constant. So if the kinetic energy goes down, the pressure goes down. So how is this related to temperature? Well, let's find out. P equals 2/3 n over volume times the kinetic energy. But because it's an ideal gas, we also know that PV, the volume, is equal to n kBT. So P is equal to n kBT over volume. So we can plug that in for P right here and solve for the kinetic energy. So n kBT over volume is equal to 2/3 n over volume times the kinetic energy. So this n cancels with this n, this v cancels with this v, and what are we left with? We are left with the fact that 3/2 kBT is equal to the kinetic energy. So, the temperature really is a measure of the kinetic energy of a particle. Because as the temperature goes up, the speed goes up. The kinetic energy increases. If the temperature goes down, that means that the speed is lower. So the temperature and kinetic energy are directly related. And so we can think about the temperature being caused by the kinetic energy of the particles, and then the resulting impact they have on the container gives us the idea of the pressure. Okay? It really helps to think about what's going on microscopically with this. And if this is the kinetic energy of one particle, so the kinetic energy of all n particles is equal to this times n, because there are n of them. Okay, so that would be 3/2 n kBT. The whole reason, again, why I went through this derivation was to show how the pressure depends on the kinetic energy, and how the kinetic energy is a measure of the temperature. and vice versa. So what is the temperature? The temperature is really a measurement of the speeds of the particles. The higher the temperature, the faster the particles are moving in your container, okay, or whatever situation you're talking about. So we'll go into a bit more detail on energy next time and move on to other ideas of thermodynamics.